Alright guys, welcome to your review test study guide. I'm going to go ahead and go through the even problems on this one, and then I'll let you guys hit up the odd ones. Alright, so let's begin here. I'm going to do number 2. Alright, so the first thing that we're going to do is we want to start by changing this thing into radical form. And when we do that, basically what we're going to do is we're going to put the denominator of the fraction power there, right there. And then we're going to put the numerator portion out here. Okay? Everything else that's in the parentheses is actually just going to end up going right inside of the radical there. Alright, so what we're going to do then is we're going to break down this number here, 32, into its prime factors. So let's go ahead and do that. Now if you were to break down 32, what you're going to end up with is 5 2's. And if you break down x to the 15th, well, that's going to be 15 x's. Now, you may not really need to do that. You may be able to do this part mentally, but let's save the x's for a minute because I'll show you how to do it mentally, but if you want to actually write it out, you can. But basically, we're looking for groups of 5, right? And so for every group of 5, I can take that number out and cross it off, right? Now, if I have 15 x's in there, how many groups of 5 is that? Well, there would be 3 groups of 5 x's. And so for each group of 5, I could take 1 x out. So I could take out 3 x's. Okay? Now the longer way to do that would be to actually write out all 15 x's, which you're welcome to do if you want. And we're looking for groups of 5, so there's 1, 2, and 3 groups of 5. So that's why I took out 3 x's. Okay? Put that in parentheses, and so that's the end of my cube root there. All right, but we still have this power out here, and we can also simplify that triple x there just to be x cubed. And then we're going to go ahead and do the power. So we're going to do 2 to the 3rd power, which is 8. And if you have x to the 3rd power, and you raise that to the 3rd power, it becomes x to the 9th, because you multiply those powers together. And so there's our final answer there for number 2. All right, let's go ahead and take a look at our next problem. This one we want to solve the equation. All right, so when you're solving equations that have radicals in them, the first thing you want to do is get rid of any numbers that are outside of the radical. Now for my problem here, number 4, I don't have any numbers outside of the radical, so I'm going to skip that. But after you get rid of any numbers that are outside the radical, the next step is to raise both sides to a power that matches the root. So in this case, I have a 3rd root, so I'm going to raise both sides to the 3rd power. 2 to the 3rd power is 8. And in this case, the 3rd power cancels out the 3rd root, and we're left with this. And then we're going to minus 3 on both sides, and then we're going to divide by a -1. And there we have it. All right, so I'll let you guys handle number 3, and we'll go ahead and move along to the next problem. Number 6. Now, number 6, we're being asked to solve again, but this time we're being asked to solve an equation that involves rational exponents. So the first thing we want to do is we want to get rid of the numbers that are not under the influence of the power. So in this case, my 8 doesn't have any power affecting it, so I'm just going to move that to the other side here. What does that give me? -256. And then there's also a -1 here sneaking in front of that x, so we can get rid of that because that's not being affected by the power either. It's just multiplying the x. So now I'm left with positive 256. And now the way that we get rid of that power is we're going to raise both sides, and this is the next step after you get rid of everything outside the influence of the power. You get rid of the power, And you do that by raising both sides to the reciprocal power. Okay? And so those cancel out when you do that. And now I'm left with the following. All right, and we can simplify that. 256 to the 3/4 power can be rewritten as the 4th root of 256 being raised to the 3rd power. And so we want to find what number multiplies by itself 4 times to make 256, or we could just go about it the longer way where we just kind of start breaking it apart. What goes into 256? That's 128, and then 64, and then 8 and 8, and so on. And I know 8 is 3 2s, so I'll just save myself some trouble there and do that. And so basically it looks like we have 8 2s that make up the number 256. And all these things are being multiplied together. And we're looking for groups of 3. I'm sorry, we're looking for groups of 4, my bad. So here's a group of 4, and here's a group of 4. So I could take out 2 2s. Now, at this point, we got to be a little bit careful. Anytime you have an even number here, you're going to be getting 2 answers, a positive and a negative. Okay? So really what we have here then is a positive and a negative 4. And we're cubing that. So 4 to the 3rd power is 64, and negative 4 to the 3rd power is 64. So we end up with 2 answers on this one, plus and minus 164. So for these types of problems, anytime you have an even root, just know that your x that you're solving for is going to have 2 outcomes, a positive and a negative. Okay? Let's go ahead and move on to our next problem. Number 8. For this, we're graphing. So basically, we need to start by remembering that when you're graphing radicals, you have a number out here. You have a number here, and here, and here. And these two numbers put together, taking the opposite of this, like we have for quite a few different functions now, is going to comprise what I'll call the starting point. This number here is going to determine whether our graph is going to go right or left. It's right when it's positive, it's left when it's negative. And this number here is going to determine whether we're going up or down, and once again that's positive versus negative. So the first thing I want to do is I want to rewrite this so it fits the format appropriately. So first of all, I've got a negative 1 in the front. Second of all, when you have a number in the front here and a number here, you need to factor that number in the front out. So I'm going to divide a 2 out of there, which would leave me with this. And I don't have my k, which if h or k are missing, then it's 0. Okay, so I've rewritten it so that it looks a little bit more like it should. And now I'm ready to graph it. So my starting point is going to be, oh, and by the way, this is a cube root. My starting point is going to be negative 2 and 0. And since my graph is going to the right and down, it's going to look like this. Now that's if it were a square root. Cube roots look a lot like square roots. It's just that they have one extra thing. They also go in the opposite direction as well. Okay? So we started off by just following what we get from here, which is right and down. But since it's a cube root, it's also going to have that symmetrical half to it. Now when you guys do number 7, yours is a square root, so you're only going to have the original half. You're not going to have the reflected half. So graphing this then, my starting point is negative 2, 0, right and down. And like I said, if we were just doing a square root, that's where we would stop. but with a cube root, we're also going to do this. And then we're good to go. That's the graph. All right, let's go ahead and we'll move on to our next problem, number 10. Solve each equation with the quadratic formula. Okay, so quadratic formula can only be used when you're dealing with a quadratic equation, which is what this is, and it has to also be equal to 0. All right, and so this is my A, this is my B, and this is my C. And we're going to do x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we'll just plug everything in where it goes. Okay, so this is 100. And then this is going to make negative 256. Now, since I'm subtracting a negative 256, it's actually going to be plus 256. So I've got 100 plus 256, which is 356, all over 8. And at this point, we want to simplify our root a little bit. So let's break it down. It's a regular old square root, so we're just looking for pairs. I know 2 will go in there because it's an even number. And it looks like I can do that again. Then I end up with 89. I don't think anything goes into 89 if I'm not mistaken. I think that's a prime number. And so at this point, I would just go ahead and say, okay, we have negative 10 plus and minus. Oh, I didn't finish doing my square root, did I? I did it in my head, but I forgot to write it down. So we have 2 2's. I could take a 2 out. So the square root of 356 becomes 2 square root of 89 over 8. And the last thing we need to do, if we can, is if you have all 3 numbers present, so you have to have all 3 of them present, and they can all be divided by something in common, which they can. All of those can be divided by 2. Then you're going to go ahead and do that. And that's just like reducing a fraction, basically, is what you're doing. And there's our final answer for that one. Okay. Let's go ahead and move on to the next one, number 12. Rewrite the quadratic equation in vertex form. All right. So for this one, step 1 is to, well, let me kind of remind you guys of what we're even trying to do here. This is what's called standard form. And what we want to do is we want to transform it into vertex form. And it requires us to go through this somewhat of a lengthy process that involves something called completing the square. All right? So the first thing you're going to do is you're going to minus the constant number to the other side. The next thing you're going to do is you're going to factor the leading coefficient out. So I'm going to divide a 2 out of both of my terms here. Oh, I forgot my y. Sorry about that. That needs to be in there. Then we need to complete the square. And that's kind of a weird and new step. So let's chat about that for a minute. I'm going to take this number here in the middle, the negative 4. And the first thing I'm going to do is I'm going to take half of it. Now half of negative 4 is negative 2. And then I'm going to square it. And that means I'm going to multiply it by itself. What's negative 2 times negative 2? Well, that's 4. And then I'm going to add it in right there. So half, square, and add. So I'm going to add a positive 4 right in there. And that's what we call completing the square. And the reason we do that is because that little process creates for us what's known as a perfect square trinomial. So that when we factor it, we get the same factor twice, which means I can write it as a square, which is what we're trying to get to. So that's why we do all that. Now the problem though is that by putting a new number in here, I just made the equation not equal anymore. The left side was equal to the right side, but I just added something to the left side. So if I want this equation to stay balanced and accurate, I need to add something to the other side also so that it stays equal. So how do we do that? Well, you might think, well, we put 4 on the left side, so let's just put 4 on the right side. Well, it's not quite right because this 4 is really being multiplied by 2. So by putting a 4 in there, we actually put 4 times 2 on the left side, which is 8. So here's how you fix your balance. You take the number here, and you're going to multiply it times the number you added inside the parentheses. And then you're going to take that new result, which is 8, and you're going to put that number over here. And that's what will keep it balanced. Our next step is to factor this side. Now you could use the box method, which we've been talking a lot about in chapter 6, or you can use the shortcut, because I shared with you guys a shortcut last time that we did this lesson. And the way the shortcut works is you're always going to have an x here and a square here. And the only thing that's ever going to change is the number that comes after the x, and it will always be half of this number, so it's just going to be minus 2. So if you wanted to, you could do the box method, but this is much faster. But mind you, that shortcut will only work for perfect square trinomials. Okay, it doesn't work for all of them, so that's why I didn't really do the box on that. All right, next one we have -3 and 8 can be added together to make 5. And the last step is to go ahead and just take this 5 and subtract it on both sides. So if we subtract the -5, if we subtract 5 on both sides, then we would have this as a result. Okay, and so back when we did this lesson, we wrote down some actual verbal steps to help you with that if you want, but there was a nice little reminder of how to do it, and I'll leave you guys to do number 11. All right, let's go ahead and move on to number 14. For this particular problem, we're being asked to find the rate of change on the average rate of change on a certain interval. Now, just so you guys know, rate of change is just a fancy word for slope. And the way we calculate slope is we do y2 minus y1 over x2 minus x1. Okay? So, they give us our function, where f of x represents our y value. And this is not a point. This is an interval. And we're starting here at -3, so I'll call that x1. And then we're stopping here at 2, which I'm going to call x2. So the first thing I want to do is I want to find out what is f of -3. That'll give me my y1, because if you plug in x1, that'll tell you y1. And then I want to find my y2 by plugging in my x2 value, which is 2. So let's go ahead and do that. So y1, if I plug in -3 to my formula up here, is going to end up being the following. Squares are first. Then comes multiplication. And then addition and subtraction from left to right. So my y1 is 5. Let's go ahead and find out what our y2 is. So now I'm going to plug 2 into the same equation there. Once again, squares are first. So both of these are 8 by multiplication, the next step. And subtraction from left to right is going to give me 15. So now we have y1 and y2. We have x1 and x2. And all we need to do now to find our rate of change, or slope, is plug it into my formula here. So y2 minus y1 over x2 minus x1. Okay, in this case, those become positives because it's double negatives, and we're left with 10 over 5, which simplifies to 2. So there's my rate of change. And then finally, what we need to do is interpret that as an increase or a decrease. Now, since my slope on average is positive, that would mean that on average, on this interval, the function is increasing. So we would call that an increasing function. If it was negative, then we would say decreasing. Okay? So I'll leave you guys to do number 13, and we shall move on to number 16. On number 16, we're going to review how to graph absolute value functions. The way that we do that is we want to remember the form of an absolute value function. Absolute value functions look like this. This number here, once again, we take the opposite of the h, represents my vertex, and this number here represents my slope, so to speak. But with absolute value functions, instead of just being rise over run, it's rise over run in two separate directions. That way, when you connect the dots together, you get a V shape. Okay? So you got to remember when you do your run on an absolute value function, you run to the left and to the right. Now, we have another situation to think about here. Notice how we have a number in front of our x, but over here we don't. So we need to fix that, and we're going to fix it in a way that's kind of similar to the other problems that we've looked at. You always start by factoring that number out of the pair that they give you. Now, something that we don't do with most other functions, but we do with these absolute value functions is, at this point, we're going to separate that 2 from the x plus 1 in its own little separate set of absolute values. And then we're going to take the absolute value of 2, which is 2, and then we're going to multiply these together after doing that. So here's what I have as a result. Okay. Now, another thing you may notice is that we're missing the plus k, but anytime you're missing an h or a k, it's just 0. So now that I've gotten my equation to match the proper format there, we're ready to graph it. So my vertex is going to be negative 1 and 0. So I'm going to go left 1 and put a dot. Now my slope is 4 over 1. So that means I'm going to go up 4, and then I'm going to go to the left 1 and to the right 1. So up 4, and then so I'm going to go up 4, and then I go left 1 and right 1. And that gives me 3 dots. And then I'm going to connect those 3 dots with my V shape, and there we have it. That's the graph of the absolute value function. All right. Continuing on, let's go ahead and take a look at 18. All right, describe the transformations necessary to transform the graph of f of x into that of g of x. So for this one, it's a multiple choice question. Slide this over a little bit so we can see the rest of it. All right. So basically what they just want to know is that, you know, if I call this my original function and I change it to this, what kind of transformations will have occurred? Well, a little while back, I gave you guys a list of transformations, and it might be something you want to have out, once again, for this exam. I'll bring it up for you guys real quick here just so you can kind of see it. And so here it is. It's from our 3.2 notes. So if you want to look back in your notebook at lesson 3.2, you should have it there. But we had a list of vertical transformations, and we had a list of horizontal transformations as well. So that'll come in pretty handy here. So let's go ahead and take a look. So now, as you can see here, if I wanted to turn this into this, basically I just need to put I need to multiply it by a negative 1/3. So negative 1/3. Now both of those do something. The negative does something and the 1/3 does something. So what do they do exactly? Well, you got to look at those sets of notes that we had. So I'm going to go back to those now. First of all, I want you guys to notice that horizontal transformations are things that happen inside the parentheses. And for this particular problem, it's not happening inside the parentheses. Okay? Inside the parentheses would look more like this instead. That would be an inside the parenthesis change. But what we have is different. What we have is outside the parentheses. Now, there's no parentheses here, but if you wanted to put in there, they would be like that. So in other words, it's not inside the parentheses. So when it's not inside the parentheses, it's not going to be these ones. It's going to be the vertical ones. So we're going to go back to the vertical transformations here, and we're going to look. So we have a negative in front of our function, right? We're taking the x squared and we're making it negative, first of all. That's going to flip the graph upside down, or another way of saying it is across the x-axis. Another thing that we're doing is we're multiplying it by a 1/3. And so 1/3 is less than 1. And so when you multiply your function by a number less than 1, you end up with a vertical compression. A vertical compression. So there is our explanation. We're looking for the option that tells us that we have a vertical compression and also a reflection across the x-axis. So let's see if we can find one of those there. There it is, option C. The negative causes a reflection in the x-axis, and the multiplication by a 1/3 causes a vertical compression. All right, so there's that. Similar question is coming up next here on number 20. On this one, they're going to give you a graph, and you have to decide what sort of transformations are those, and then you got to pick out which one of these is the correct equation. So it says write g of x, which is the dashed line. So that means that this green dashed line here represents g of x. Write g of x in terms of f of x, which is going to be the blue line. Now, I do like the way that they word their question here, but I know that it doesn't probably make a lot of sense to you guys. So when you see this, it's good to think about it, and I'll explain why they said it that way in a minute. But for now, it might be more helpful if you guys think about it this way. What would you have to do to the blue line to transform it into the green line? Or if you're not looking at a colored picture, you could say, what would you have to do to the solid line to get the dashed line? But that's the idea there. Well, first of all, as you guys can see, they're going in opposite directions. So I would have to take this blue line and I would have to flip it over this way, like that, right? So it would have to flip the opposite direction. So that's one transformation I would have to do. I'd have to take that blue line and just flip it over in the opposite direction. So that's like a reflection across the y-axis. So I'm going to write that down. We want to reflect it across the y-axis. But that still doesn't quite do it, because as you can see, it's a little bit lower than the other one. So what could I do to fix that? Well, in that case, what I could do is I could take this blue graph and I could stretch it vertically by pulling it upwards. So if I were like stretch it upwards, right, then it's going to land right on top of that green line. So it could be a vertical stretch. Now, here's the funny thing. On these graphs, a lot of times, if it's a vertical stretch on a graph, then it might also be a horizontal compression. Just the opposite. Now why is that? Why is that? Well, if you guys think about it, if you take a graph, like let's say I have this line here. Well, I'm going to redraw that. If you take this graph and you vertically stretch it, then that will make it grow taller, right? So that's one way to make it have that particular shape to it. But another way is to compress it horizontally. It's just a smaller version of it, but as you can see, it looks like it's steeper now. So to compress it horizontally makes it look taller, or stretching it vertically makes it look taller. So whenever you're doing this sort of thing, basically, if you guess vertical stretch, just know that a horizontal compression is an option as well. In the same way, if I told you vertical compression, that could technically be the same thing as a horizontal stretch. All right, but anyway, that's enough gabbing about it. So the first thing you want to do is just think, okay, rephrase the question. What would you have to do to the blue line to get the green line? And the conclusion we've come to is we would have to flip it over across the y-axis, and then we would either have to do a vertical stretch or a horizontal compression, so it would look a little bit taller like that. And now we have to find which one of these do that. All right? And so a reflection across the y-axis is whenever your function has a negative inside the parentheses. So I see two options that have that. So right now we can get rid of these. So I know it's got to be either B or C. Now the next thing is it would have to be either a vertical stretch or a horizontal compression. Now this would, a vertical stretch is where you have a number multiplying outside your function, and that number is less than 1. I'm sorry, greater than 1, my bad. So for this one here, we do have a number outside the parentheses, outside multiplying it, but it's not greater than 1. So this would actually not be a vertical stretch. That would be the opposite. So the answer would be this one. A vertical or horizontal compression is what it turned out to be instead. That's where you have a number inside the parentheses, and that number inside the parentheses is greater than 1. That's a horizontal compression. Okay, so that's pretty much the gist of it there. I'm going to let you guys handle number 19. And that does it for our little review session there. So hopefully that was helpful, and we will see you guys next time.